The purpose of this video is to discuss systems with linear and quadratic equations, but before we can do that, let's remind ourselves what a system fundamentally is. So to begin with, I'm going to draw a graph. Okay, then I'm going to consider two equations. So I'm going to draw my system brackets, and I'm going to consider the equation y equal to negative x plus 2, and then y equals maybe x plus 3. So I'm going to draw rough sketches of those in my graph. So let me go ahead and put in my tick marks. So I have y equals x plus 3. So if it's plus 3, I'm going to put my y-intercept there. I know that it rises 1 and runs 1, then rises 1 and runs 1, so I'm going to go ahead and sketch in that line. Alright, let's do the same thing for y equals negative x plus 2. So I know that it crosses the the y-axis at 2, and that it has a slope of negative 1, so it's going to rise negative 1 and run 2. So that's going to look something like this. Okay? So I could solve the system by substitution and consider the fact that I have a y here and a y there, so that means that x plus 3 is equal to negative x plus 2. So let's go ahead and write out that equation, x plus 3 equal to negative x plus 2. Then I can just add x to both sides. Now I have 2x plus 3 equal to 2. Subtract 3 from both sides. Alright, now I have 2x equal to negative 1. I divide both sides by 2. Now ultimately get that x is equal to negative 1/2. Okay? Given that I have that, I can just substitute negative 1/2 into either of the two equations. So let me go ahead and do that. I'm going to choose y equals x plus 3. So I'm going to do y equals to negative 1/2 plus 3. That's the same as negative 1/2. 3 can be written as 6 over 2. So that means that y is equal to 5/2. So let's go ahead and take all of this and zoom out and put it over to the side. Maybe make it a little bit bigger. Okay. So the idea is that the final solution to our equation, to our system of equations, is as follows. So negative 1/2, comma, 5/2. That's the same as this point of intersection. That point of intersection is also negative 1/2, comma, 5/2. And it makes both equations true. Let's see that. So maybe I'll get green for a second. And I'll take this, bring it over. Let's look at this first equation. So I'm going to put in 5/2 for y and negative 1/2 for x and see if it makes that equation true. So I'm going to write 5/2 equal to negative 1/2 plus 2. 5/2 is equal to negative 1/2. I can write 2 as 4 over 2 because 2 goes into 4 2 times. Okay, so this becomes 5/2 equal to 1/2 plus 4 over 2. Now I have 5/2 equal to 5/2 as I desired. So I know that my first equation is true. So now let's verify that the second equation is true. So I'm going to call this process check 1. Now I'm going to check that second equation. So is it the case that 5/2, substituting that 5/2 in for y, is equal to negative 1/2 plus 3? So is that equal to negative 1/2 plus 3? Well, I know 3 can simply be written as 6 over 2, so now I have negative 1/2 plus 6 over 2, which in fact does equal 5/2. So the idea is, if I'm verifying that I have the correct solution to my system of equations, if I put in negative 1/2 for both values of x and 5/2 in for both values of y, then I should get a true statement. Graphically, the solution to a system of equations is the point where those two equations intersect. So this is just sort of a quick review of some of the concepts that you probably learned in Math 1 and in Algebra 1 regarding solving systems of linear equations. In Math 2, we're more interested in the following idea. So suppose that you have some graph, and one of your functions is a parabola, or is represented by a parabola, and another of your functions is a linear equation, a line, then the parabola and the line might actually have two intersections. So you have one solution and another solution. We want some algebraic process, oops, didn't mean to do that, should have put solution 2. We want some algebraic process to take the equation of this parabola and take the equation of this line and find the points where the two curves intersect each other. Let's look at that with a real-world example. So suppose we're thinking about the price of tickets and the number of tickets that are sold. Maybe you're in charge of a theater and you're trying to figure out how much you want to charge for tickets. So there's a very clear relationship going on. So if your tickets are $5, you're going to have a lot of people come. But if your tickets become more expensive, you're going to have much fewer people come. So you're dealing with the fact that if you have more people, you're probably charging less for tickets. But if you charge a lot for the ticket, then you're going to have less people come. So let's try and get an equation for this. So notice the difference between each of these values in tickets is about $300. So difference between these two is 300, difference between these two is 300, and so on. So it seems like we're dealing with some kind of a linear equation. So let's go ahead and start by getting our slope. So let's pick our slope. Let's do 2300 minus 2000 over 5 minus 10. Oops, let me change my color there. 5 minus 10. So where we're getting this from is ultimately the slope formula. We're taking y2 minus y1, so y2 minus y1 over x2 minus x1. Okay, so if we simplify that, we get 300 all over negative 5, and that's going to be equal to negative 60. Okay, we're going to estimate that our y-intercept is going to be 0, 2600. Where did that 2600 come from? Because we don't see it on this table here, so we're increasing by 300 each time, so $10, we have 2,000, increased by 300. $5, we have 2,300. Therefore, if we had $0, we would expect around 2,600. So that's going to be our y-intercept. So we can ultimately get this equation. So let's write it as a function. So the number of tickets sold based upon the price of those tickets is going to be equal to 2,600, what we start with, and then we're going to lose 60 people for every increase in price of $1. So how would we get a function for our overall income? So let's take all this and consider that. So income is simply going to be whatever the price is times the number of tickets that you sell. But thankfully, we just came up with a linear function for the number of tickets that you sell. It's right here. It's 2,600 minus 60p. So we can substitute all of that in for t. Okay, so let's go ahead and box this off and write out our final function. So income, as a function of the price of your tickets, is going to be p times 2,600 minus 60p. So this is a nice situation where if you wanted to determine your total income, you could simply put in the price, and this function would spit out how much money that you would make. So we're going to take this result, this function, and continue talking about it in terms of a system of equations. So our ultimate result from the last slide was we had this really nice function for income, and we could put in the price of tickets, and it looked like P times 2,600 minus 60p. So just for clarity, let's go ahead and distribute that p out. So let's have 2,600 p minus 60 p to the second power. All we did is we took this p, multiplied it by this term, then have this p, multiplied it by that term. Pretty simple enough. So if you wanted to, this thing on a graph is going to basically look like this. So let's just sketch a little graph. And let's say that this axis represents P, and this axis represents your income, I. Okay, so it looks like this. And there's some maximum here that would represent your maximum income. So it's pretty easy to figure out what that is. We could just find the vertex of this parabola. So I know I can find the vertex of a parabola by doing negative b over 2a to find the x-coordinate of the vertex. And I would get negative 2600 over 2 times negative 60. And if I did the math on that, I would get out around 21.7. Okay? So that tells me that I should charge about $21.70 for each ticket. And it would be okay for me to find that total income by putting in 21.7 into my function. Oops, it's kind of a weird 7, sorry about that. And I would set that equal to 2600 times 21.7 minus 60 times 21.7 raised to the second power. So that's just putting this value, this price, into my function. And if I calculated that, it would spit out the following income. About $28,000 and $28,166. So if you're just looking at it from this perspective, it's a relatively easy problem. We just have to come up with an equation relating the income to the price of tickets, but real-world situations usually are not this convenient. Normally in a real-world situation, you don't just figure out what you're going to make profit-wise by thinking about your income. You also have to factor in your operating cost. So let's suppose for a second that we had some function for operating cost. Maybe I want to call that function O. And O is going to be a function of P, price of my tickets. So let's think about what this fundamentally is going to mean in terms of what this function O does as far as increasing or decreasing. So let's think about the fact that we know that as the price of my tickets increase, that the number of tickets that are sold decreases. And that makes sense. The more you charge for tickets, the fewer people are going to come. If you have fewer people attend, your operating cost is going to go down. You don't have to pay for as much if you have fewer people attending your event. So let's review that. The price of the tickets goes up, the number of tickets that we sell then would go down. Then the number of tickets that we sell decreasing means that our operating cost is also going to decrease. So if we take all this, we can summarize that by saying, the more I charge for my tickets, the less I have to pay in operating cost. So we're going to expect this function O to decrease. Let's think about it as a decreasing linear function. So let's say that the base value of my operating cost is going to be $17,500. But for every dollar that I raise my price for, so for every dollar I raise the price of a ticket, I have to pay $50 less in operating cost. So now I have this interesting situation where I have a function I that represents how much money that I bring in, and I have this function O that represents how much I have to pay to run my business, period. So my question is going to be, what's the break-even point? At what point do I spend as much money running my theater, paying my employees, paying for materials, paying for a movie, as I actually take in from ticket cost? At what point do I spend as much as I make? And at what point do I net $0? So we're going to think about that a little bit more heavily in the next slide. At the top of the screen, I've written the two functions that we've talked about for most of the video. And my question is, what is the break-even point? At what point does my operating cost equal my income? So let's think about that. My question is, at what price, as far as what I'm going to sell my tickets for, is my operating cost going to equal my total income? Well, if O of P is the same as I of P, I think I'm just going to call both O and P and Y of P. Maybe I'll just call them Y. And now I'm going to take that information and I'm going to set up a system of equations where let's say y equals 2600p minus 60p squared, and y equals $17,500 minus 50p. So we've done all of this work ultimately to arrive at this system. Now in our next slide, we're going to try and solve it. So in the top left-hand corner of my screen, I have my system. So I've never solved a system before where I have a quadratic equation and a linear equation. So that's a big part of math too, is trying to understand how do we solve systems that contain more than just linear equations. So let's recognize that y and y are clearly the same thing. They're the same number, they're the same value. So if y is equal to this left-hand side, and this left-hand side is also equal to y, then this thing must be equal to that thing. So let's go ahead and set that up. Now I have 2600p minus 60p squared equal to 17,500 minus 50p. So let's think about how we're going to solve this thing. I would like to get a quadratic equation in the form that I'm used to, which is ax squared plus bx plus c. Maybe I'll write that at the top. I would like something in the form 0 equals ax squared plus bx plus c. So I'm going to have to force this thing to be in this form. So let's start by taking this 17,500 and subtracting it from both sides. So if I subtract 17,500 from 17,500, it's just going to go to 0. And then I'll also subtract it from this side. So I'm going to rewrite this as negative 60p squared plus 2600p. All I've done is just reorder these two. So 60p squared comes last, now it comes first, doesn't matter. Now I'm going to subtract this 17,500 from the left-hand side. 17,500 is no longer on the right-hand side because we've subtracted it. And now I'm going to take this negative 50p and bring it down here on the right-hand side. So now I have this, negative 50p. Okay, I'm getting a lot closer to having 0 on one side of the equation. So now I'm going to add 50p to both sides, just like I subtracted 17,500 from both sides. So I'm going to add 50p to this. Alright, not too bad. So now I'm going to get negative 60p squared plus 2,650p minus 17,500. And now it's equal to 0. So a lot of work, but now I'm at a point where I have a quadratic equation. So let's do one thing to make this look a little bit simpler. So I'm going to take all of this and zoom out. Alright, so I recognize that I can divide negative 10 into each value. So negative 10 will go into negative 60, negative 10 will go into 2,650, negative 10 will go into negative 17,500, and negative 10 will go into 0. So if I can divide all of these by a factor of 10, I'll have a much simpler problem. Excuse me, by a factor of negative 10, I'll have a much simpler problem. So that would make this, oops, let me write, 6p squared minus 265p plus 1,750 equal to 0. So this would be the quadratic that we would need to factor, but it's going to be very difficult doing that using the box method. It's going to be very difficult doing that using completing the square. I would recommend that you use the quadratic formula. Because I don't want to make this video any longer and I don't want to detract from our main concepts here, I'm going to go ahead and write out the final answer to this. If you would like to for practice, you can definitely put this into the quadratic formula and verify the answer that I get. So I'm actually going to get that p is equal to two values. So for this equation above to be true, p can equal 8.08. So, oops, terrible 8. So 8.08 or 3608. So let's remind ourselves of the context of this problem. The whole point was to find our break-even point between when we knew that we were going to get the same amount of money in income as we would have to pay to run the business. So this is telling us that if I charge $8.08, I'm not going to make any money, I'm not going to lose any money. If I charge $36.08, I'm not going to make any money, I'm not going to lose any money. In our last slide, we're going to think about that on a graph. So here's our graph, and we're going to let the independent axis represent P, the price that we charge for tickets. And let's let the y-axis, the dependent axis, represent either the money that we are spending in our operating cost or the money that we're receiving as we charge for tickets. So our income function, which we created, it was I of P, was just some parabola. And we went ahead and found the maximum of that. We found that, assuming that we weren't thinking about operating cost, that when you charge $20.67 in your price, you would make a maximum total income of $28,166. But we kind of threw a wrench in the situation when we started thinking about operating cost. We knew that if the price of tickets was zero, that we would have to pay $17,500 in operating cost. But as the price of tickets increased, the operating cost was decreasing. And we reasoned that that was because the more we charge for tickets, the fewer people were going to come. So we found these two break-even points, here and here. The points where the function I of P, represented in blue, was equal to the function O of P, represented in purple. So at this point, the first one, operating costs were the same. Or excuse me, was the same as our income. And we found that that point was when we charged $8 and I believe 8 cents per ticket. And then we had this other situation. This other situation where operating cost and income were equal to each other. And that was the situation where we charged $36.08 per ticket. Okay? So we've done a lot of cool things in this video. We've built functions that relate operating cost to price of the tickets sold and income to the price of tickets sold. And we've used this new idea of a system with quadratic equations and linear equations to answer some pretty interesting questions about break-even points and what we would need to charge if we wanted a certain outcome in a real-world situation. So that's going to conclude this video, and I'm going to give you guys some practice on solving systems and building functions, specifically solving systems where we have at least one equation that is nonlinear. That will conclude this video.